Pluto, a far-off and obfuscating world, was once a solitary, fair planet, an individual from our planetary family. In any case, unsettling clarifications by leading astrophysicists Neil deGrasse Tyson and Michio Kaku brought Pluto back into the spotlight with a shocking revelation. They suggested that this cold world is on a potentially loaded trajectory with Neptune. But how could this happen, and what might be the consequences of such a massive event? Are we witnessing an extraordinary cosmic anomaly, or is there more to this impending, endless disaster? Join us as we assess the potential consequences of a Pluto-Neptune collision. Pluto, a former planet that was demoted to a smaller, dwarf planet, mostly due to its eccentric orbit, remains a subject of interest and debate in the cosmic community. According to precise calculations by leading experts, Pluto's orbit is dangerously close to Neptune's. Leading astrophysicists Neil deGrasse Tyson and Michio Kaku are both raising concerns about a potentially hazardous collision between these two celestial bodies, which could pose a significant threat to Earth. But how is such an event even possible? Pluto's journey around the Sun is unlike any other planet in our solar system. It takes an astounding 248 years to complete a single orbit. This means that, since its discovery in 1930, Pluto has not even completed one full revolution around the Sun. But the intrigue doesn't stop there. Pluto's path is defined by its highly eccentric shape, making it vastly different from the nearly circular orbits of the larger planets. What makes Pluto's orbit even more perplexing is its inclination, measured at 17 degrees to the ecliptic plane. The way Pluto moves is dramatically different compared to other planets. This inclination and eccentricity add layers of complexity to its orbital model. One of the most fascinating aspects of Pluto's orbit is its interaction with Neptune's. For about 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, defying what we would expect from their positions in the solar system. This raises a natural question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational effects of various planets. The study of Pluto's orbit began shortly after its discovery. Initially, astronomers struggled to make sense of its unusual path. Unlike other planets, whose orbits lie relatively close to the ecliptic plane, Pluto's orbit stood out with its extreme inclination and irregular shape. The key to understanding why Pluto's orbit doesn't intersect Neptune's lies in the stability of Pluto's path, despite its complexities. This stability is a testament to the intricacies of celestial mechanics. The three-body problem in space refers to understanding how three objects, like Pluto, Neptune, and the Sun, move and interact with each other through gravity. It's like trying to predict where they will go based on where they start and how they pull on one another. In Pluto's case, this problem shows how its orbit, Neptune's orbit, and the Sun's gravity all interact in a complex manner. Terms like asymptotic libration scope, and VZK wobbling are part of this problem. According to astrophysicists, what keeps all planets in their orbits is a type of libration. In Pluto and Neptune's case, this means that whenever Pluto crosses Neptune's orbit, its position is always at least 90 degrees away from Neptune. This spatial separation is critical in preventing their orbits from interfering with one another. Degree libration, on the other hand, refers to the vertical movement of a celestial body in its orbit. For Pluto, this means that when it comes closest to Neptune or another giant planet, it is positioned far above their orbital plane, adding an extra layer of protection from potential collisions. Another crucial factor in this scenario is the VZK wobbling. This is named after three researchers, V.A. Zverev, L.V. Kovalenko, and K.U. Dovankov, who studied how celestial objects move in space. It's about how three objects, like Pluto, Neptune, and the Sun, pull on one another with their gravity. This pulling influences how they move. For Pluto, the VZK wobbling helps explain why its path near the Sun is so unusual. Despite appearing chaotic, this wobbling plays a role in maintaining Pluto's orbit over incredibly long periods. These factors help maintain Pluto's orbit, ensuring it doesn't collide with Neptune or deviate from its stable path. This three-body problem is crucial to understanding how these orbits shift due to gravitational interactions. Understanding these dynamics also helps us study our solar system and distant stars and planets. Numerical simulations in the late 1980s revealed that, despite these stable properties, Pluto's orbit is chaotic, with minor deviations in starting conditions leading to significant changes over millennia. Yet, these strange properties of Pluto's orbit have been found to maintain consistency over vast time spans. Later computer models have shown how the giant planets, like Neptune, Jupiter, and Saturn, affect Pluto's orbit around the Sun. Neptune has a unique relationship with Pluto, where for every 2 orbits Pluto makes around the Sun, Neptune completes 3. This resonance helps keep Pluto's orbit stable. But Neptune isn't the only factor. Jupiter's gravity also plays a significant role in stabilizing Pluto's orbit, with Saturn contributing as well. Simulations show that Jupiter's gravity alone is strong enough to ensure Pluto remains on a stable path for an incredibly long time, possibly billions of years. Perhaps Neptune, Jupiter, and Saturn are working together to keep Pluto moving safely in space without running into trouble. These complexities are essential in the broader context of the universe, maintaining order and stability in celestial mechanics. Without these factors, the solar system as we know it would be a place of much greater chaos and instability. For Pluto specifically, with discussions about a potential collision with Neptune, understanding its orbit is crucial. It gives us a clearer picture of the solar system's dynamic nature. The case of Pluto illustrates how even the most seemingly unstable orbits can achieve harmony through the intricate interplay of gravitational forces and orbital mechanics. The case of Pluto serves as a reminder of the immense complexity of celestial dynamics. Even with modern tools and advanced simulations, the stability of its orbit continues to astonish scientists. This stability, despite Pluto's eccentric and inclined path, highlights the resilience of the solar system's intricate gravitational dance. Astrophysicists emphasize that orbital resonance, the synchronized relationship between Pluto and Neptune, plays a pivotal role in maintaining this balance. Without such resonance, it's plausible that Pluto's irregular orbit might have led to catastrophic interactions with Neptune or even an ejection from the solar system altogether. The bigger picture. The study of Pluto's orbit not only deepens our understanding of this distant dwarf planet, but also provides critical insights into how gravity shapes the universe. The principles at play in Pluto's trajectory are not isolated phenomena. They echo throughout the cosmos, influencing the behavior of exoplanets, binary star systems, and even entire galaxies. For instance, many exoplanets discovered around distant stars exhibit eccentric and inclined orbits, much like Pluto's. By studying Pluto, scientists can refine their models of how planetary systems evolve and how they manage to remain stable over billions of years. This knowledge helps us identify planets in the habitable zone, regions where life as we know it could potentially exist. Moreover, understanding the mechanics of orbital stability is critical for assessing risks within our own solar system. Although a collision between Pluto and Neptune is exceedingly unlikely due to the safeguards of resonance and libration, studying these interactions prepares us for potential scenarios where celestial bodies might deviate from their paths due to external forces, such as rogue planets or gravitational perturbations. Future exploration. Pluto's status as a dwarf planet has not diminished its significance in the scientific community. The New Horizons mission in 2015 provided humanity with the first close-up images of Pluto, revealing a world rich in geological diversity and dynamic processes. Scientists now know that Pluto has a surprisingly complex surface, with vast ice plains, towering mountains, and even possible subsurface oceans. As technology advances, future missions may focus on exploring Pluto's orbit in greater detail, perhaps even deploying probes to study its interaction with Neptune and other celestial bodies up close. These missions could uncover new details about the gravitational interplay that governs not just Pluto's path, but the broader architecture of our solar system. Final thoughts. Pluto's story is one of resilience and intrigue. Despite being demoted from planetary status, it continues to inspire curiosity and debate. Its orbit, eccentric, inclined, and seemingly chaotic, defies initial expectations, yet it remains stable due to the complex interplay of gravitational forces. The lessons we learn from studying Pluto extend far beyond its icy surface. They remind us of the delicate balance that governs the universe and the intricate mechanisms that maintain order amidst apparent chaos. As we continue to unravel the mysteries of Pluto and its orbit, we not only deepen our understanding of the solar system but also gain insights into the workings of the cosmos itself, the broader context of Kuiper belt dynamics. Pluto's role in the Kuiper belt is crucial to understanding the outer reaches of the solar system. The Kuiper belt, a vast region beyond Neptune, contains countless icy bodies, dwarf planets, and comet-like objects. These objects are remnants of the early solar system, providing a window into its formation and evolution. Pluto, as one of the largest and most studied Kuiper belt objects, KBOs, serves as a gateway to uncovering the mysteries of this region. Its gravitational interactions with Neptune are not unique. Many smaller KBOs are also influenced by the gravitational pull of Neptune, leading to resonances similar to Pluto's 2:3 orbital resonance. These relationships help stabilize the Kuiper belt, preventing objects from scattering or colliding on a large scale. The possibility of planetary migration. One of the most intriguing theories about the solar system's past is planetary migration. Models suggest that, in its early history, the gas giants shifted positions, with Neptune moving outward and disrupting the Kuiper belt. This migration could have pushed Pluto and other objects into their current orbits, explaining their high inclinations and eccentricities. If such migration occurred in the past, could it happen again? While the likelihood is minimal over human timescales, the possibility cannot be entirely dismissed. Gravitational interactions with passing stars or massive interstellar objects could trigger shifts, potentially destabilizing the current resonance between Pluto and Neptune. Could Pluto be a threat to Earth? Although a direct collision between Pluto and Neptune is unlikely, could such an event indirectly impact Earth? The gravitational disruption caused by such a collision could send debris into the inner solar system, potentially threatening Earth. Additionally, if Pluto or another Kuiper belt object were ejected from the solar system, its gravitational influence could disturb the orbits of smaller bodies, such as asteroids, increasing the likelihood of impacts on Earth. Studying Pluto's orbit and its relationship with Neptune allows scientists to model potential chain reactions in the solar system. This knowledge is essential for predicting and mitigating future risks posed by gravitational instabilities. Future missions to Pluto and beyond. The New Horizons mission was a groundbreaking achievement, but it raised more questions than it answered. Future missions could focus on more detailed studies of Pluto's surface, atmosphere, and internal composition. Additionally, spacecraft equipped with advanced instruments could study the gravitational interactions between Pluto, Neptune, and other Kuiper belt objects. Exploration of the Kuiper belt is also a priority for understanding the solar system's outskirts. Missions designed to study multiple KBOs could reveal patterns in their composition and orbits, shedding light on the processes that shaped this distant region. The role of technology. As computational power increases, scientists can create more accurate simulations of Pluto's orbit and its interactions with other celestial bodies. These simulations are essential for understanding long-term orbital dynamics and predicting potential disruptions. Advanced telescopes, both on Earth and in space, will also play a critical role in monitoring Pluto and its neighbors, ensuring we remain vigilant about any changes in their behavior. Final reflections. Pluto, once considered a lonely outpost of the solar system, has become a focal point of scientific discovery and wonder. Its dynamic orbit, complex relationship with Neptune, and position in the Kuiper belt make it a key player in understanding the solar system's past, present, and future. The study of Pluto extends beyond its status.